Hi everyone, I am Pawan Tiwari. I'm a PhD student at Grants Science Institute. Today I'm going to talk about the multi-wavelength view of gamma ray burst afterglows. So gamma ray burst, or the GRBs, as we know, these are the MEV transient events that results from the merger of two compact objects such as a neutron star or a neutron star with a black hole, or the death of the massive stars. From the observation, we know that the GRB has the two main emission episodes, which one is the highly variable prompt emission, which you see in red in color, which is followed by the long-lasting afterglow, which spans across the electromagnetic spectrum from radio to high-energy gamma rays. While the prompt emission is interpreted as the internal shocks between the different part of ejecta, while the afterglow results from when your jet interacts with the intermediate medium around the burst progenitor. So the afterglow gives you a very critical insights about the profile of a medium. Plus, it gives you also to understand the microphysical parameters which can govern the shock dynamics of afterglow. Also, it helps us to understand the kinetic energy which is left after the prompt emission has happened. So that's why it's very important to study afterglow, because it can gives you a very wide picture of the shock dynamics. Here in this slide, I'm showing you a multi-wavelength light curve of one GRB 130427, where you can see the data from radio to MEV. However, I would like to draw your major attention to the major breakthrough happens in the field of afterglow, when in 2019, first time, the MAGIC and HESS has reported the very high energy photon from two different GRBs independently, proving the fact that GRBs can be the source of very high energy photons, means like TV photons. With all these advancement, but the limitation of these IACTs, imaging atmospheric Cherenkov telescopes, till so far, we have detected finally 5 GRBs in very high energy domain. The emission in the high energy gamma rays corresponding to the GeV are a little bit, they differ from both the thing. Also the shape, the spectral index also differs. So they can give you the knowledge about what can be the radiation mechanism which plays role there, such as whether the synchrotron is there or the SSC. Also, since as I mentioned before, we have seen only 5 GRBs so far. So either these very high energy GRBs are having a unique population, or also they are a part of the standard population, but we cannot see due to the limitation of our imaging IACTs. So using all these, I would like to answer these questions with this given study. So what I did is I do a multi-wavelength study of these GRBs, having the afterglows observed by the Fermi lat in the GeV energy range. So for that, what I use the publicly available data from the SWIFT and Fermi across 16 years of operation, starting from the Fermi operations till 2024. In a brief introduction about these two telescopes. So the SWIFT has 3 main instruments, which operates from UV range to the hard X-rays, meaning to 150 keV, while the Fermi Gamma Ray Space Telescopes has two telescopes on board. One is GBM and the LAT. For this study, I use only the high energy gamma rays, which operates from 30 MeV to 300 GeV. With this study, I would like to first of all answer what is the most dominant radiation mechanism which is playing role there. Also, can be considered some microphysical parameters such as the magnetic field, or let's say the slope of the injected non-thermal photons, which can constrain the shock dynamics. Plus, can we also comment on the medium around the burst progenitor, as we know that the long GRBs comes from these Wolf-Rayet star, so there should be a wind medium. Can be constrained on that, or the profile of the medium is homogeneous. With that, I would also like to answer the question whether these GeV afterglows can also emit the very high energy emissions, but we cannot see just because of the duty cycles. So just how I choose my sample. So since we are interested in the simultaneously observations of the afterglow, so from these 16 days of observation, with these criteria, I found only 31 GRBs with the 74 time bands is being selected for this criteria. I also excluded the flaring state because there is a study which said the flaring state in the GRBs correspond to the prompt emission. So to avoid those anomalies, I choose only the GRBs which having the typical standard afterglow. Also, I included the hard X-ray data from the back. I performed the time-resolved spectral study. I would like to compare the two observables, such as the energy flux X, which gives you the let's say the emission in the given energy ranges and the spectral indices. First of all, I'm showing you here the comparison between the emission in the given energy ranges. So on y-axis, we have the emission in the high energy gamma rays corresponding to 0.1 to 10 GeV, while on x-axis for both the plots, for the right hand side, we have a narrower energy range, which is from 0.3 to 10 keV, corresponding to the Swift XRT telescopes. On the y-axis, on the other plot, I have quite broader energy range, which correspond to 0.3 to 150 keV, which is corresponding to the Swift XRT plus BAT, means you have a broader energy range there. So what we notice here in a right plot, we see if we compare between the narrower X-ray and the high energy gamma rays, we see the flux is systematically higher in the is systematically higher in the X-ray energy ranges. However, if we increase our broader X-ray part, we see that these data are distributed around the equality line. So this is due to the fact, because of the choosing of the energy ranges, we can see this kind of a feature. The next observable we would like to compare was the spectral indices, meaning that I would like to compare the hardness, the nature of the hardness in a given energy range. So again, here on y-axis, we have the spectral indices computed in the high energy gamma rays from 0.1 to 10 GeV, and on x-axis, we have 0.3 to 10 keV, the X-ray one. What we observe, there is a clustering of these photon indices. So the first one, which correspond to the harder X-ray, shown by green in color. What does this hard X-ray means? Like you have in a given energy range 0.3 to 10 keV, you have more harder X-ray photons. For these harder X-ray photons, the GeV emission is softer. This is the typical spectra of what looks like for these kind of photon indices, the populations. The next is the one which corresponds to the moderately harder X-ray emission, corresponding to this red color, and the typical spectra of these GRBs looks like this, meaning that you have the GeV emissions also harder. Is the best example where you can see the inverse Compton losses playing role there. And then the third lines where you have a softer X-ray emission in a blue color, and the typical spectra looks like this, where you have a softer X-ray emission, but whatever will be your GeV, you can see there is a double spectral component there. So these are all the, let's say, the observed we have found with this study. Now we want to explain this, how we have explained it. We simulated a sample of 220 GRBs having the different energetics and placed at a different redshift. Why we choose these 220? These 220 number mimics the number of the detected by the Fermi GBM in 1 year. And the values of E, ISO, and jet are not selected randomly. They have been taken from these papers, which they have done a rigorous study. What we would like to with this simulated one, we want to find out, as I mentioned before, I would like to find out a set of microphysical parameters, such as the prompt efficiency or the fraction of energy which goes to accelerate the photons or given to produce the magnetic field. To find out whether with these microphysical parameters, can we explain the X-ray and the GeV emission? So for that, I use the self-synchron code based on the Lemach model to get my observable flux plus the spectral indices in the given energy range, X-ray, GeV, and VHE. So since we have to start over these microphysical parameters, so since there have been previously independent studies which has done in the X-ray and even in the high energy gamma rays, where they show there should be a clustering of a light curve data points in the observable rest frame of those GRBs. There's some correlation exists. So there's the sky blue one correspond to the Avanzo 2012, where they show that in the X-ray energy ranges, there is a clustering of a light curve exists. Similarly, in the high energy gamma rays too, where those has been represented by the lines, the magenta and the pink lines, the lines only. These are the correlation which has been existed before. So first of all, I would like to find out, can we do this simultaneously? can find some set of parameters which can simultaneously explain both the independent correlation. So yes, we found with that, if we choose the synchrotron self-Compton and in the wind medium with these parameters, with these given parameters, the slope of non-thermal injected photon 2.2, the prompt efficiency 10%, and the value of epsilon b that is to produce the magnetic field the lower 10 to the power 4, we can explain both the simultaneous observation. So I would like to just to take home message from this slide is just if we want to explain both simultaneously the X-ray and high energy gamma rays, we require the lower density wind medium and also a lower magnetic field to explain both the observation, to both the clustering. So since we found these parameters, and next we would like to check for the observed, what we have observed for our study. So here is again the same plot. The emission on y-axis is the high energy, and on x-axis we have the different X-rays. So the blue shaded region is 1 sigma confidence, where you can clearly see, like with a given set of parameters, we can explain both in the both energy domains. Mostly the most part of we can explain both these. So however, you will see that there are a few data points on the top of which you cannot be explained with these parameters. It is just because they are facts, because we choose the bulk Lorentz, the typical bulk Lorentz factor for the GRB around 300, but these are the data points corresponding to the GRB having the higher bulk Lorentz factor around 500. So that's why you cannot explain those. Plus also these are very early time observations, so they can be the prompt contaminated. So you cannot, that's why you cannot explain those. But if you go for lower data points, which is mostly corresponding to really afterglow, where is you have very less prompt confirmation, you can explain all these observations. Next, since we have explained all these observations, so I would like to whether we can predict the very high energy emissions from the GRB afterglow. Yes, we choose those parameters which we have found before, and we predicted this very high energy emission. Since we know that for the TV, we have observed in the TV that the very high energy flux, the intrinsic very high energy flux corresponding to is comparable to the intrinsic. So we would like to compare in the two given ranges. So what we see, yes, here again the correlation exists between the very high energy and the X-rays. Also for comparing, I choose the data points for two GRBs detected in the very high energy domain, 190114C and 190829A. So yes, we can explain this, but there are three data points which we cannot explain with this. It's also the same fact because this GRB has a very highly bulk Lorentz factor, and this is the very early time observation, so it cannot come inside the predicted band. So I'm just with the summary. This is the summary of my work. So since we have these 31 GRBs which having the simultaneously observation between the soft X-rays and between the X-rays plus the high energy, in order to explain both the simultaneous observation, we would like to inquire to have the inverse Compton losses. Plus, since as I mentioned, like since these are the long GRBs which favors mostly wind mediums can also be proven by this study. Like these parameters more favors these observation more favors the wind-like medium with these typical microphysical parameters. Especially, I would like to mention like we will require a lower magnetic field just because would like to have more inverse Compton losses to explain the high energy gamma rays with the X-rays. Using that, we also predicted the intrinsic very high energy flux, which very correlates very well with the X-ray, and it's consistent with the previously TV detected GRBs. Here is the paper we have submitted the last week. If anyone, they can check it out. Most importantly, I would like to say like what we can do with this study. So since we find out a set of microphysical parameters which can explain both the observations. So what we can do, these can help us to produce, these parameters can help us to produce the VHE light curve, which can help us to design the observational strategy for detecting the very high energy photons for the GRBs with the current and future these ICTS with the, let's say, with the tile pi or something. And I would like to do it further. And since we are collaborating with Monica for these things, so hopefully this work is coming published soon. Thank you so much.